Let's see. All right. Okay. Welcome back. Lecture 7 in statics. I hope everybody had a relaxing 3-day weekend. First off, first question, did you bring a scientific or graphing calculator with you? That's what I like to hear. One thing I will mention before we begin is that my lecture today is going to revolve around the use of a specific calculator. I'll show you what I mean. Like, I have a little emulator tool to emulate a particular calculator. It's the Casio, the one that you see here. If you have that Casio or a similar Casio, the operation should be probably very similar. If not, if you have a TI calculator like a TI-89 or something like that, if you access the Microsoft Teams channel for this class, I posted a list of like 5 different YouTube videos that I found that will show you how to do the operation we're going to talk about today. It's pretty straightforward, and I would only say that the operation that we're going to do today, I would learn how to do it on your respective calculator because it's going to save you a ton of time on homeworks and exams. In terms of other announcements, so attendance grades are up to date, and we're rocking and rolling on the homework structure. So homework 2.2 is graded, 2.3 was due today, and homework 2.4 is assigned today. Okay? Any questions? Yes, sir.
With the 2.2, it was graded like 2 days ago or whatever, but it like disappeared from the grade book.
It should be on there now. That's a fair question. That was on me. Usually what I like to do is that was on me is I'll turn the grade column off, let the TAs have a chance to grade it, and then turn it on so that everybody sees it all at once. I forgot to turn it off. So what happened is it was on, then it turned off, and it turned on. They're all up. So yeah, that's a fair question. So that was just on me. Didn't get a chance to do it. So, but yeah, everything should be graded and up to date now. So everybody good? That's a good question. Okay, the reason for the bringing of your calculators is because your calculators will make simple a necessary mathematical task that we're going to have to do periodically throughout the semester, and that is the solution of systems of simultaneous equations. We're going to start with 2x2 systems because we're going to start dealing with 2-dimensional problems, and then we'll enter the 3rd dimension here in a couple of lectures. But I want to recap this process because here's the thing. Everybody in here has done this type of problem before. And so let me recap what we're talking about. It's probably been a while since you've done these types of problems, but let's sort of bring it back to square one. So what I'm talking about is a problem like you see right here on the screen. Let me color this in, like a colorful, font here so you see what I'm talking about. Okay, so we have 2 equations, and I just made these up. There's nothing special about them. But we have x plus 2y equals 3, and 2x plus 3y equals 4. And so the goal in this type of problem is to find those magical values of x and y that satisfy both equations, okay? And so there's a graphical corollary to this problem. Like, let's take the first equation, x plus 2y equals 3, okay? I could rearrange that equation by bringing x onto the other side, so 2y equals minus x plus 3, and then dividing both sides by 2. So this first equation is really just the equation of a line rewritten. Like, I could take equation 1 and write it in y equals mx plus b fashion, right? I can do the same thing with the lower equation. Really, these are just 2 lines. And so what I'm trying to do is find that point at which they intersect, right? That's what the 2x2 system is all about. In fact, there is an entire course of mathematics devoted to this type of problem, and it is called linear algebra. So, like for instance, I know the electrical engineers, they're required to take linear algebra. And if you're ever interested in some upper level stuff in engineering, so if you've ever heard the term finite element analysis, you civils, really anybody, civils, mechanicals, biomedicals, finite element analysis is all built on the solution of simultaneous equations and linear, and understanding of linear algebra really does help with that. But going back to what we're talking about here, so this type of problem is going to show up today and very quickly in the field of statics. Now, I want to go back into a mathematics land solution of this type of problem. There's really three different types of approaches that you could use that I would consider practical. The two that you're probably most familiar with are substitution or elimination. And to be crystal clear, you could use those on these problems in this course, and I have no problem with that. The downside to substitution and elimination with the problems that we're talking about in here is that very rarely do you deal with very, pretty constants, like 1 and 2 and 3. Usually it's like the cosine of 52 degrees. So it's this weird, irrational decimal that goes on forever. And so usually the most practical approach is to use matrix algebra. In other words, what your calculator will do for you. So, but I want to go back to square one to show you how this stuff works and what you're familiar with, okay? So let's review the first method, which is substitution. So I've got the system, the original system written up here. So let's review substitution. So the way that substitution works is I pick one of the expressions and I solve for one of the variables. So let's, or one of the equations and solve for one of the variables. So let's isolate one of the variables in the first equation. So I have x plus 2y equals 3. What I'll do is I'll get everything that's not x onto one side of the equation. So what this equation is telling me is that x equals 3 minus 2y. And what I'll then do is I'll take the second equation, this one over here, and substitute that in. So what I'll do is in the second equation where it says 2x plus 3y equals 4, instead of x, I will put in this, what the first equation told me x equals, right? And so do a little bit of algebra, a little bit of arithmetic, chug and chug and chug, and bam, I get y equals 2, okay? So how do I get that? Well, what do I do here on this second line? 2 times a pile of junk, multiply 2 times each term. So 2 times 3 is 6. 2 times negative 2y is negative 4y. And so I've got 6 minus 4y plus 3y equals 4. Combine the like terms. Negative 4y plus 3y is negative y. 6 minus y equals 4, which means y equals 2. And now that I've got a value for y equals 2, I can take that value, substitute it into really either equation, it doesn't matter. I'll put it into the first one, so x plus 2y equals 3. Instead of y, put in 2. Bam, I get x equals negative 1. There's the answer, okay? So that is the magical value of x and y, respectively, that will satisfy both expressions, okay? And if you don't believe me, just plug and chug. Look at the top equation. X plus 2y equals 3. What's negative 1 plus 2 of that? It's 3, right? What about the second expression? 2 of this and 3 of that. 2 of that's negative 2, 3 of that's 6. Negative 2 plus 6 is 4. So that's, you can very easily see that that set of values satisfies both equations. And one of the tenets of linear algebra is that there is only one set of values that satisfies both equations. So take linear algebra, that's like the whole point of the class is determining that and trying to understand these types of systems, whether matrices are singular or invertible, all that stuff. It's great stuff. Okay, that's method one. Any questions? All right, method two is elimination. Method two is really what sort of begins the process of understanding linear algebra. So what I do with elimination is I say, okay, let's take one of the equations and multiply the whole thing by a scalar, okay? So what I'll do is I'll take the first equation and let's keep it simple. Let's multiply the whole thing by negative 2. So instead of x plus 2y equals 3, I get negative 2x minus 4y equals negative 6. It's like, well, fine, but why'd you do that? The reason or the goal is to try and match the coefficients in the other equation. So if you look at the x terms after I did all that, I got a negative 2x in this equation and a positive 2x in the other equation. So what I do is I take the first equation and the second equation and I add the whole thing together, the whole kit and caboodle. So I take the constants, add them together, the y terms, add them together, the x terms, and add them together. And the idea is to match the coefficients so that if I add this up, okay, so negative 6 plus 4 is negative 2. That's a typo. So, yep, that's a typo. Whoops. So that's supposed to be negative 6, negative 4. That's supposed to be negative 2 there. Whoops. So we'll add that to the mistake counter. So yeah, that's supposed to be -2. Whoops. I'll fix that in the slides and re-upload. So -6 and 4 gives you -2. -4y and +3y gives you -y. But look what's going on with the x's. -2x and +2x, those cancel. Those are eliminated. Hence the name of the term, or the name of the method, elimination. And so then what I can do is take that value of y. I can either do the elimination process again, or I can substitute. It doesn't matter, and I still get the same process or the same result. Okay, does that make sense? Barring my little typo on my slide. So, okay. Now method 3, depending upon your background in linear algebra, some of you might already have a background, some of you might not at all. Matrix algebra is a way of standardizing this process. Okay. So the way matrix algebra works is the first thing that I do is I rewrite the system, okay? So I rewrite the system in matrix form, okay? And I'm not going to make you all do matrix multiplication or anything like that. I just want you to kind of understand the process. So the idea is that I rewrite the system in this fashion. So what I have is a matrix of coefficients times this column matrix. Another name in matrix algebra for a column matrix is a vector. So if you ever, in matrix algebra land or linear algebra land, a vector is a column matrix. So that's another definition for a vector for the mathematicians. So I put the variables in this matrix and the terms on the other side of the equals over here. So this square matrix over here is just the list of coefficients. So if you look at the first line where it says x plus 2y, I have 1 and 2. I have the 1 because there's, a 1 on the other side there. We just don't write it. And so on the bottom row, I have 2 and 3. So 1, 2, 2, 3. So that's my square coefficient matrix. That's my unknowns. And that's my resultant vector on the other side. And so the idea using matrix algebra is that if I wanted to solve for x and y, what I would do is I would invert this matrix. So basically multiply both sides by the inverse of this, and so x and y would be the inverse of this matrix times that. And if you plug and chug that in matrix algebra land, you will get -1 and 2. So you will get the answer that you're looking for. I'm not going to expect you to do that part by hand. I'm going to expect you to do that using your calculator. This can be kind of laborious for systems that are larger than 2 by 2. If you get into 3 by 3 land or even 4 by 4, that gets really tough to do by hand. It's not impossible, but it starts to get really, really tedious. And so this is where your calculator will come into play. So let me show you how this is done on the calculator. And I'll actually pull up a calculator emulator here in a second to show you how this works. Now every calculator is going to have a little bit of a different mode. I'm going to pull up the Casio and show you how this is done. But basically, whenever you're using your Casio, just doing regular old calculations, you're in mode 1. Mode 1 is the computational mode. If you hit the mode button, which is on the top, there's a little mode and it says setup over there on the right. You should see a menu that kind of looks something like this. What I'll do actually, let me turn on the lights because I know that you all are looking at your calculator. It might be a little easier to see this to where you can actually see it and it's not dark in the room. Is mode 5 is the equation solver. And so there's various options that the Casio gives you. For instance, mode 3 in equation is the quadratic equation. Mode 4 is the cubic equation. But what you're looking for, I'm getting a phone call on Teams. We'll call them back. Sorry. Okay, so mode 1 and mode 2 are what we're going to be after. Mode 1 is a 2 by 2 equation solver. Mode 1 is 2 by 2. Mode 2 is 3 by 3. So what you're going to do is you go to mode, or option 5 to go to equation solver, and then option 1. And when you do that, you should get a window that looks something like this. And what you're going to do is populate this table with what you see here on the screen. And what you see here on the screen is just me replicating this. So, 1, 2, and then 3 for over here on the end, 2, 3, and then 4 here on the end. And once you press equals, you should get x equals -1 and y equals 2, which is the solution to the system that we've been looking at. So let me hit escape and actually do that with you. So here's my calculator. I'm going to go to mode 5, 1, and here's that editor. You can see that editor right here. I've got a little pop-up display that's kind of bigger. And we'll do 1, 2, 3, 2, 3, 4. And so once you do that, hit enter. There's x is or equals. X is -1, equals again, y equals 2. And so it's pretty straightforward there. If you've got your Casio with you, that's how you do it. If you are using a calculator that's not a Casio, that's a TI or something like that, again, I posted to Teams, I think it was like 5 or 6 different videos for assortment of calculators. Most of them were TIs. I think I did like a TI-36X, a TI-84, a TI-89. I think I did a TI Inspire. I think I even did an HP calculator. So there should be more than enough calculators that represent the vast number of people in this room. Does this make sense, this concept? Anybody have any questions about this idea? Everybody good? Okay. All right. I'm going to turn the lights down again so that we can go back to the presentation. Sorry. And I actually want to talk about statics. I'm sure some of you are like, what do you mean, Dr. Mike? You've been talking about statics for the past 2 weeks. Actually, no, I haven't. If you actually follow what I've been talking about over the past couple weeks, it's been mathematical preliminaries, physics preliminaries, and we've spent the past few lectures just defining what vectors are and how to add them together. But we haven't actually talked about statics. So let's talk about statics. Now, on day 1, I defined for you the difference between statics and dynamics. Now, I want to see if anybody in here was paying attention. If you had to tell me what statics was, or what's the difference between statics and dynamics, can anybody in here give me a simple, straightforward definition between statics and dynamics? Yes? What's that? Static situations don't move. So that's a very simple but pretty straightforward answer. Static situations are involving bodies that are either at rest or at a constant velocity. The big thing is that static systems do not accelerate. And if they don't accelerate, and Newton's second law says that force and acceleration are proportional, then the sum of forces are 0. So up until now, we've learned how to add forces at a given point, and we can express this using our new IJ notation. So remember, the resultant vector is equal to the sum of vectors at a given point. And if I wanted to write that in IJ notation, what I could do is I could say the sum of the forces in the x direction times I, the sum of those magnitudes, plus the sum of the magnitudes of the forces in the y direction times j. That could be a resultant, okay? Now what we're ready to do is introduce statics. And what statics states, remember, Newton's first law says that an object that is at rest or at motion will remain at rest or at motion until acted upon by an outside force. Objects that are in static equilibrium are static. They are at rest. For static systems, the resultant must be 0. Okay? Now, from a theoretical perspective, what we've been doing for the past couple weeks has been kind of boring because all we've been doing is just adding vectors. Now we're ready to start doing some analysis. Now what we're ready to do is look at a situation and see what are the forces necessary to maintain or to achieve static equilibrium. That's what we're after. And that's really the first step in a lot of engineering mechanics analyses, whether it's a bridge, a gear, a pacemaker, I don't care. In order to design those systems, what we first are looking at are what are the forces required to keep that system in static equilibrium. That's sort of where it all begins. So how does that relate to what we've been talking about for the last 10 minutes? Well, often to solve for unknowns, what we do is we go back to that IJ notation. Remember, the resultant says that the sum of the forces equals 0. And if I look at that resultant in a 2D perspective, I have the sum of the forces in the x direction times I plus the sum of the forces in the y direction times j. That has to be 0. So what do I end up dealing with? A system of equations. 2 equations, 2 unknowns. The sum of the forces in the x direction has to be 0. The sum of the forces in the y direction has to be 0. So whenever we're looking at static equilibrium in 2 dimensions, 2 equations, 2 unknowns. Now this is assuming that we're dealing with statics of a particle. Later on, when we look at statics of rigid bodies, we're going to add something to this. We're going to look at the sum of moments on a body. But we don't have to worry about that because all the forces all go through a common point. Now, the best way to learn how to do this is to do some problems. But before we do, we got one thing we got to bring up, and that's this. This is not going to affect our example today in class. This will affect your homework assignment. So remember, we are dealing with let's go back to what we're talking about here. This is a course in engineering mechanics. And if you remember, mechanics is the study of forces, okay? We are dealing in forces. If I give you a problem and I say you've got this 50 kilogram mass, that should spark a fire in your head. Say, whoa, mass. Mass that's not a force. Weight is a force, okay? So automatically I need to convert that. Remember, the weight of an object is equal to its mass multiplied by the acceleration due to gravity, okay? So in SI units, we can take that as 9.81 meters per second squared. And in U.S. customary units, we can take that as 32.2 feet per second squared. So whenever you're dealing with a mass in this course, make sure that you're converting that to its weight. This is a really easy thing to get tripped up on. You could do the entire problem correctly and forget this. So don't forget that. All right. Many problems are going to reference an object's mass instead of its weight. So make sure that you handle that. Bless you. Any questions? Now, like I said, this is not going to affect the problem that we do here in class. This is going to affect your homework problem. So make sure that you remember that. Okay, the best way to learn this stuff is just start doing problems. So we're going to do a problem right now. I have this, a particle here, and we're going to determine the forces required to achieve static equilibrium. So let's read the problem, and let's see if we can identify the particle, and let's see what's going on. So I have a box here, or a weight, and this weight equals 400 pounds, and it's being supported by two cables, okay? And I've got these various angles here, and the idea is, what are the tension in the two cables required to ensure that the block is in static equilibrium? So I've got two cables, so I'm basically solving for two forces in these cables, okay? I'm going to have two equations and two unknowns. The two unknowns are the tension in this cable and the tension in that cable. The two equations are the sum of the forces in the x direction must be equal to 0, and the sum of the forces in the y direction must be equal to 0. Question, what's the particle? What's the point at which all of the forces are going through? C. C is the particle, right? Remember, this is statics of particles, so all the forces are going through C. We got a tensile force going that way, tensile force going that way, and a weight going that way. So what we're going to do is we're going to introduce a concept today called a free body diagram. Basically, that's just taking the problem and resolving it into its most base components. The forces, the distances that affect the equations of equilibrium that we're going to write. So that's sort of a way of simplifying what's going on. We're going to take these vectors, define them, write them in IJ format, sum the forces in the x direction, sum the forces in the y direction, solve the system. Okay, let me move some stuff out of the way. Let's bring up the notebook and get to work. Okay, so here's the problem. The first thing I'm going to do is I'm going to write this, draw this free body diagram. I think that free body diagrams at this point are a little bit of a formality. Later on, they're going to be very essential in solving more complex structures. So let's draw that out. So free body diagram. Now before I draw this free body diagram, we're drawing the free body diagram of point C. So let's see if you all are paying attention in terms of your measurements and whatnot. Can somebody tell me what is this angle right there? There we go, 50 degrees. Is that measured from the horizontal? Yes. What about this angle? 30 degrees. Okay, so if I look at point C, So let's say that's point C. I've got three forces that are essentially going through point C. I have a force going like that. I have a force going like that. Let's name these. Let's call this the tension in cable AC and the tension in cable AB. Did I forget one? Yeah, what did I forget? The weight. And which way is that acting? Straight down. And so I'll draw that one in a different color because I know that one. And then just to make sure that the diagram is complete with all the information that I need, this is really all I care about. That's all I need to really solve this problem. Okay. Now, everybody okay with this? Okay. If you're okay with this, then what we need to do is we need to write descriptions of the vectors. Okay, so I'm going to put this over here. I'm going to put description of vectors in IJ notation. Okay. Let's start off with vector TAB. Okay. So let's take our time with this. So TAB is going to be Apollo junk times I plus Apollo junk times J. And we know that, right? Let's see if we can fill in that Apollo junk. Let's start off with signs, with positives and negatives. The I component, should it be positive or negative?
Negative.
Negative. It's going in it's in quadrant 2, right? Negative X direction, positive Y direction, right? So this is going to be negative. That's going to be positive, right? Okay? Now, how do you determine the X component? Let's go back to what we've done before. You take the magnitude times what? The cosine or the sine for the X component? Cosine, right? So could I write the X component as the magnitude of this vector times the cosine of 50 degrees? Would that be a fair way of describing that component? Magnitude times the cosine. And so over here, it'd be sine of 50 degrees, right? And we can use that plug and chug, cosines with the x and sines with the y, because we've written the vectors and we've written the angle in such a fashion that it's referenced from the x-axis. Is everybody okay with that? That's not too bad, right? One easy thing to forget when doing this are the magnitudes. You still got to have a TAB on each component. Don't forget that. Okay? So, if we've done this, let's do the next one. What about TAC? So, Apollo junk times I plus Apollo junk times J. Somebody help me out with the signs. Or what do we got? Positives, negatives? What's the deal going on there? They're both positive. Exactly. All right. Somebody help me out with this. What do I put in here? Anybody? TAC cosine 30. And the next one's going to be TAC sine 30, right? Not too bad, right? Again, the idea is that this stuff's going to get a lot more systematic as the semester approaches, or semester goes on. So far, so good? Did I forget one? The weight. There we go. We forgot that. So let's do the weight. So the weight is going to be Apollo junk times I plus a pile of junk times J. What goes in here? 0. What goes in here? What's that? Mass times. Well, true, but the problem gave it to us in pounds, so we don't have to do the conversion. But I'm glad you're thinking that. So let me scroll up. Okay? So 0 goes in here. What goes in here?
Negative 400.
There you go, negative 400. Somebody said 400. If you said 400, take your hand out, do that. That was a joke. Negative 400 pounds. It's negative 400 because it's going down. That's a very easy mistake to make, okay? So far, so good? Any questions? I'm glad somebody said that. Make sure to maintain your signs. So far, so good? All right. So now what we can do is we can look at our equations of static equilibrium. So equations of static equilibrium, there are 2 of them, right? Sum of the forces in the x direction must be equal to 0, and the sum of the forces in the y direction. But here's the reason I love IJ notation. Sum of the forces in the x direction equals 0. Isn't that all the I stuff? Isn't that just all the stuff being multiplied by I? I mean, what is this term? That's the magnitude along the x direction times I, right? Same thing with this. Same thing with this. So what I can do is say, what is this equation if I write it out? What is the sum of the forces in the x direction? It is negative TAB cosine 50 degrees plus TAC cosine, one too many parentheses, 30 degrees plus 0 is 0. Again, the sum of all the stuff in the x direction must be equal to 0. What about in the y direction? Just sum up all the stuff on the other side. So what do we have? Plus TAB sine 50 degrees plus TAC sine 30 degrees minus 400 pounds is 0. Do you see how I went from here to here? You see how I did that? Again, I'm just collecting all of those coefficients. That's the beauty of IJ notation, is that the coefficients associated with I are the magnitudes of the forces in the x direction. The coefficients associated with J are the magnitudes of forces associated with the y direction. All right. So here's our 2 equations, 2 unknowns. A lot messier than what we had before, right? A lot messier than x plus 2y equals 3, right? So what I'm going to do now, does everybody have this? Are you okay if I scroll a little bit? Okay. So what I'm going to do is I'm going to rewrite this a little bit. Okay? Let's take the first equation. All right. Let's be clear. What are our 2 variables? TAB and TAC, right? So what we're going to do is we're going to rewrite this and we're going to maintain our order. And you're going to see what I'm doing here in a second. So there's a reason I'm writing it this way. So the first equation, I'm going to say TAB times a coefficient, minus cosine 50 degrees, plus TAC times a coefficient, cosine 30 degrees. And then I'm going to take all of the other numerical constants, move them to the other side of the equation. And so since there are none, this is 0. And then for the second system, I'm going to sort of do the same thing. TAB sine 50 degrees, TAC sine 30 degrees. And then that 400 pounds, I'm going to move this to the other side of the expression, and I'm going to say 400 pounds. Okay? So all I'm doing here is taking this system and reformatting it a bit. The reason I'm reformatting it this way is because if you look inside these parentheses, that's what I'm going to put in my calculator. Okay? I'm just maintaining the signs in a structured fashion so I don't lose where the positives and the negatives are. And so now what I can do is I can say, all right, let's go to the Casio mode 5, 1. And what I can do is enter this matrix in the fashion that the Casio wants. So negative cosine 50 degrees, sine 50 degrees, zero and 400 pounds. So what I'll do is I'll sort of do that, do that, do that, do that. Now here's the thing, I keep referencing the Casio. I don't care what calculator you use, you're going to input it in this fashion. So it's going to be the same input schematic. Now, when you use your Casio is not going to spit out like TAB, TAC, etc. It's just going to spit out X and Y. One of the things that's very, very critical when you write out your equations of equilibrium is that you maintain the order. What I did when I rewrote this is I just kept everything alphabetical so that the TAB term was first, then the TAC. TAB, then TAC. And that's going to become important here in a second because the Casio, and really any of your calculators, is not going to understand like which one's TAB, which one's TAC. So you have to keep that straight in your head. And the best way to keep that straight in your head is just to keep everything alphabetical. Okay? So what I'm going to do is I'm going to break out the Casio, and we're going to solve this system. So bear with me. So we're going to go to mode 5, 1, and now we're going to start entering in this system. And so notice how this term is negative, everything else is positive, and that goes to how we wrote it up here. We want to make sure that we're maintaining our signs. So negative cosine 50 equals cosine 30 equals. You might, if you have your calculator in radian format, you might need to go back and change your mode to degree format and then come back here and do this, so make sure that you're using a consistent format. The next term is 0. Then sine 50, sine 30, which we should know that's a half, and then 400. And so what you should have is an entry that looks something like this. And then once you have that in, you press equals. And what it gives you is this. It should say X is 351.75, and then Y is 261.08. We're going to hang out a second, make sure that I did this correctly, see if anybody else is getting the same thing that I'm getting. Anybody else is getting this? There we go. All right. So what you should get is X is 351.78 and Y is 261.08. 0.08. So that's what you should get from your solution out of the Casio. One of the hallmarks that you've done this correctly is that you should get positive answers for both of them, okay? And that should pretty much be the case for everything that we do between now and exam 1. Because what we're doing is we're solving for forces that are in tension. If we got an answer that was negative, what the physics would mean is that the force that we assumed was in tension was incorrect. It's actually in compression. But that doesn't make sense from the original point of the problem. We have a weight being supported by 2 cables. I don't know if it makes much sense to have a cable in compression. You know what I mean? It's got to be in tension, so the answer's got to be positive. Okay? Now, in terms of how do we map this to an answer, well, again, the calculator doesn't know what TAB and TAC is. So what it's doing is it's saying this first variable is X, this second variable is Y. That's what it's saying. It doesn't know what TAB and TAC is, which is why when you write this out, you want to group it in such a fashion that you've got all your variables grouped together. What I tend to do is just go alphabetically. So I did AB first, AC second, okay? So what's the answer? What are the tensile forces in these cables required to achieve static equilibrium? The tensile force in cable AB is 351.78 pounds. The tensile force in cable AC is 261.08 pounds. And that's the answer. Do you have to use your Casio equation solver to do this? No, you don't. But if you didn't want to do that, you'd have to do elimination. You'd have to do substitution. And the problem is these values are messy. You know what I mean? If you want to track all the algebra and whatnot to get the exact answer, go ahead. I think it's not worth it. I think it's worth it to just let your calculator do the heavy lifting. Yes, sir? Did I? 7.9? I'm sorry. 7.5. Did I? Oh, you're right, I did. Sorry. So we'll add 0.02 to the mistake counter, or 0.03 to the mistake counter. Again, Marshall University policy allows me 7 mistakes per semester, but I'm the one who keeps the mistake counter, so I never hit 7. It's a corrupt system, I know. That was a joke. No, thank you. No, in all seriousness, like I'm a human being. If I do something like that, let me know. Because chances are, if you saw it, there's 20 other people that's like, fix that, please. And if I knew it, I'd want it fixed too. So, no problem there. Does that make sense? So yeah, and just on a side note, if you're ever interested in this whole type of analysis, if you're ever interested in linear algebra or anything, linear algebra is a great class. It's a very math-heavy class, but it's very valuable. You learn a lot of really good stuff there. But yeah, any questions about this? So let me tell you what's going to happen moving forward so that you're aware. So what we're going to do next time is we're going to do another example like this, but I'm basically going to make that problem a little more challenging, because instead of 3 forces, we're going to have 4 forces. What I will then do is we're going to add another type of analysis problem that gets thrown into the mix with particle statics, and that's pulley problems. We're going to do pulley problems next time, and then after that, we're going to enter the 3rd dimension. We're going to do 3D problems. So what is 3D going to do from a solution perspective? It's not going to make it any more difficult. It's just going to add another row and another column. Instead of a 2x2 system, we're going to have a 3x3 system. What makes 3D complicated is not the solution, not the statics. The statics is actually pretty easy. The hard part is actually describing the vectors in 3D. So what you end up having to do is you have to write a distance vector, convert that into a unit vector, and then write your force vector. And I know that seems convoluted, but trust me, it's the easiest way to go. Any questions? You are free. I will see you all on Friday. That's all I got.